You can see that black line is the course plan. Then you see it starts to build out these smoother plans right in front of it effectively to go navigate nice and smooth to that location. And so
all right. Hello, everybody. I'm Dr. Satya Malik, CEO of OpenCV. The recent advances in machine learning have not just been limited to fields such as generative art. Fully autonomous vehicles have really taken off recently, getting smaller, lighter, and more capable than ever before. Today, our guest is Chad Sweet, co-founder of ModalAI, a leader in the field. He'll be showing us the latest computer vision advances in the fascinating world of unmanned vehicles. But first, with me, as always, is Phil Nelson, Director of Content and Creative for OpenCV. Phil produces the show, and if anything goes wrong, it is his fault.
Yes, welcome to OpenCV weekly webinar where nothing can possibly go wrong. Excuse me, possibly go wrong. I'm your co-host with the co-most, the second banana who is second to none. I'm also your plus one and only. It's Mr. Nelson. If you're nasty, but you can call me Phil, and I'll be your Huckleberry. But first, I'm here to remind you of a couple things we do every single week here on OpenCV Weekly, the first of which is a giveaway to you in the audience. Later in the episode, you'll have the chance to answer a trivia question, and we will give you the OpenCV course of your choosing. You can go to opencv.org/courses to see what courses are available and buy your own. Later in the episode, you'll get to win one, including the Mastering AI Art Generation course. We're also taking questions and answers from you in the audience, so please use the chat system wherever you're watching, Twitter, Twitch, Facebook, etc., or use the little Q&A button here in the Zoom chat to ask your question at any time during the show. We will do our best to flow it into conversation as time permits. As a reminder, this show is sponsored by OpenCV.ai Consulting. Get consulting from the experts such as Dr. Satya Malik, Anna Petrovichova, Gary Bradsky. Hit them up at OpenCV.ai and check out the portfolio to see how you can level up your business. Satya?
All right, thank you. Chad, welcome to the show. And we can begin with a short introduction, and then you can share your screen and we can have the presentation.
sounds great. Thank you very much, Satya and Phil, for having me. I really appreciate it. This is very exciting. I've been using OpenCV since I would say 2006 or so. I think there was an OpenCV 1 to 2 transition around that time that created a lot of header issues, but so I've been using it for a long time. I'm glad to be here. And so I'm the CEO at ModalAI. I spent, so ModalAI is about 5 years old. Prior to that, I spent 20 years at Qualcomm, which is here in San Diego, and I led robotics R&D for about my most recent 5 years there. And then prior to that, I led computer vision R&D, the software team for developing computer vision software. So I've been working on this stuff for a long time, and happy to share what we are up to and what we see are the advances for unmanned aerial systems. And so, of course, we are May the 4th, so have to throw in. I was
really hoping you would cover that in the slides. I appreciate it.
We have the train going on in the background. Sorry about that. I'm not sure if that's coming through or not, but. So
the coaster, you mean?
Oh, yeah, exactly. That's probably the one, the coaster. And so enough about myself. At ModalAI, we're about 37 to 40 employees, mostly in San Diego, California. Largely our product, we'll talk about our products, but really I'll try and really focus on how we are leveraging computer vision, because fundamentally our main product is a computer vision processor for drones. That's really the crux of what we're building, is an highly condensed and sophisticated processing platform. And so you see that picture a lot. That's what a DJI Phantom, the flying camera use case became super prevalent in the mid 2010s, whatever we call that decade. And that really drove this big, somewhat boom, but maybe a burst of, folks going out and taking pictures at the beach, taking videos at the beach. And what became really apparent was they needed to get safer, which has a lot of different vectors on how you can improve safety. At ModalAI, we focus a lot on size. The smaller, the lighter they are, of course, the less impact they can have. But autonomy and starting with obstacle avoidance has been really the foundation of what is needed to improve this safety. So over the last, say, 8 or so years, there's just been a huge advancement, huge movement, huge trend towards putting more and more computer vision capabilities on these UAVs. And I use drone, UAV, UAS somewhat interchangeably. They're all kind of the same thing, and they get thrown around a bit interchangeably. But so it's really become the foundation of what is needed to build, a UAV in 2023. You need computer vision on your drone to go make it do something useful without causing a bunch of other problems. And so I'll give a bit of an intro here, because this kind of provides the background of what we do at ModalAI, which is really, again, build this computer vision processing platform that fuses an autopilot, which is the software that flies the drone. PX4, as Phil brought up, Ramon runs drone code, which is where PX4, which is the open source software package that performs all these flight control functions. So we have computer vision. We have a Qualcomm QRV5165 processor, which can do here. We're showing 5 AI neural networks running concurrently on the platform. All that vision is running on the platform. We, of course, focus on size. Size helps do things like indoor mapping, which we're showing here a little bit of a visual inertial odometry screen. I can jump back real quick. But here we're showing a visual inertial odometry screen, which is how this drone is navigating.
It may be useful for the audience, because some people may not be very familiar with all the terminology. So if you could explain what is visual odometry, etc., that would really help people.
Yes, thank you. Good reminder. I actually, the next 3 or 4 videos are all about how visual inertial odometry works.
Great.
So I'm probably jumping ahead a little bit. I won't slow down. I'll let the marketing part play, and then we'll go. Okay. Go into the details. But of course, size really matters for safety as well. It's really important to be small. SWAP is size, weight, and power. It's kind of an industry colloquialism. Here we're showing mapping occurring outdoors to go pursue these autonomy functions. We build our. There's me. I don't like videos of me, but there's me showing that we build our hardware in the US, which is important to a big part of the UAS industry. We build and so again, back to the indoor mapping. And we support a number of communication links as well. So which all fuses together in terms of how these platforms are actually used throughout the world. And so to kind of dive in a little bit on the spec sheet, we can ingress 7 MIPI CSI sensors. So MIPI CSI, I don't have a good example of one here. I do have the board though. For scale, you can see how small this is. But here we
cannot see because you're sharing your screen, so it's it's tiny. Yeah.
Okay, well that's not. So it's smaller than a business card.
Okay, that actually nails it.
and so these MIPI CSI. So MIPI is a standard used in the smartphone industry for image sensors, and so that's all of your iPhone, your Android, Samsung. They all have all those sensors that are sticking out the back. Those are MIPI sensors that end up going into the chip that's on board, or the SoC or system on chip that's on board that does the computer vision processing. And so this is a bit of a spec sheet, which we could go into for a very long time. I'll try and touch on the high level stuff, but here we have 8 gigs of LPDDR5 RAM, so super fast RAM. There's an embedded neural processing unit that pairs with the GPU. So there's the concept of an NPU dedicated to neural network processing, which is a big SIMD, or simultaneous instruction multiple data processor, like a GPU, but more more dedicated to like just the multiply accumulate portion of what would go into running neural networks. But we have also very nice inertial measurement units on board. There's 2 IMUs, which can be used for fusing, and we'll talk about visual inertial odometry as well. And so this is the platform, smaller than a business card, and we will get into what all that means. So on top of that sits what we refer to as our VOXL SDK. So our product we call VOXL, which if you do 3D computer vision, should be familiar with what a VOXL is. But our VOXL SDK sits on there, leverages a bunch of OpenCV to.
And if you don't know what a voxel is, think Minecraft.
Minecraft. Thank you. Yeah. And so, yeah, sorry, there's a lot of intermixed topics here. I'll try and build a story that gets us to the end of full 3D mapping and planning and voxels and the whole bit. But it's complex, so feel free to tell me if I'm missing something. But this SDK is a number of microservices that sit on top of the platform that all communicate over Linux pipes. So these services can all run on boot and then communicate over Linux pipes to share data that we've defined in these structures. And so we have depth from stereo, which we'll touch on why that's important, what that needs. We have April tag processing, we have neural network processing. Of course, we have to calibrate these sensors. We have visual inertial odometry, and then we have our VOXL Vision Hub, which kind of fuses it all together and then interacts with the flight controller, which then effectively tells the drone where to go and what to do.
Mm-hmm.
And so the big topics that have been prevalent since that 2015 period, what happened after that Phantom 3 that was shown on that image was the Phantom 4 from DJI included obstacle avoidance for the first time. And so that was probably in the late 2016 timeframe, maybe early 2017. They added this feature of obstacle avoidance, meaning if you're flying your drone and something jumps out in front of it, or you're about to hit a building, it will stop automatically. And so that was like a pretty incredible feature, because now you've got this real world application of computer vision on a drone, making the product significantly better and safer. And so another topic, you'll hear these words many times throughout my presentation, is visual or GPS denied navigation, which is another term for visual inertial odometry. And so visual inertial odometry is where you take the image data coming in, you combine it with the inertial measurement units to generate a position, really a relative position or an odometry. So it's a dead reckoning technique in 3D space. So I don't really touch on optic flow specifically, but optic flow is, in the unmanned aerial space, is somewhat of a precursor to this, because optic flow typically works in a 2D plane and works with latitude hold, whereas VIO or visual inertial odometry works in the 3D space. So it gives you X, Y, and Z. So it's a more comprehensive system, which is very valuable when you're flying, because you have a Z, you have a Z value. So you want to be tracking your altitude as well in a precise way. And so where this also, so even in a GPS active environment where you can receive GPS, VIO is still very interesting, because GPS provides about a 1.5 meter sphere of accuracy. So the UAV could be, if it's doing a great job, it could still be floating around in a bubble of about 1.5 meters, which really isn't that great. Like, you know, if you're, you know, you got, especially if it's a very large drone, you know, it's like kind of floating around in the air out there. Whereas the visual inertial odometry system, you can generally get centimeter level accuracy, meaning the vehicle can hold position to, you know, like a really tight position, like a centimeter, where you can barely even notice it's flying. We take these videos,
sort of like a hawk or a bird of prey, kind of, you know, floating on the wind there.
Exactly, yeah. And so we take these videos, and if it's not for the shakiness of your hand, you would think the drone was just stuck in the air, hanging on a string. It's really pretty fascinating. So it really enhances the experience, and then we'll talk about why that matters in the indoor space and so forth. And so here now, this is actually a ground vehicle.
Well, one
Obviously.
other question I have
yeah.
is, do you use, it's slipping my mind, there is a term for the kind of GPS where you have one unit. Is it differential GPS? What is it called?
Yeah, probably RTK or differential GPS.
Right. It is, you have one GPS unit and then you measure it with respect to that. And
Absolutely.
so you can get not sub-millimeter, about a centimeter accuracy or something like that, right?
Yes. Yeah, you can absolutely improve your GPS performance with the differential techniques. And basically the error or what creates that 1.5 meter bubble is the atmosphere interfering with the signal.
Right.
And then the receiver obviously there's a noise. It increases the noise floor. The atmosphere does, and but it does it in a consistent way. So actually, it's not increasing the noise floor. Sorry, it's adding a phase error. The atmosphere adds a phase error to the GPS signal. And so what you can then do is, if you have another surveyed station or a ground station where you know the precise position, you can measure that atmospheric interference and then subtract that from the measurement the drone is receiving. That being said, it's a lot of equipment.
Okay.
And it's more expensive.
That's true. That's true.
It's not a
and
freebie.
Maybe I'm not 100% sure, but maybe it may not be as accurate as visual, because here you're latching on to features, right? Which could be very, very accurate if the scene is not changing. Is that correct?
Yes, in a relative sense, VIO and computer vision perform very, very well, but there is a drift, so it's generally 1 to 1.5% drift over distance. So if you're looking for like accurate survey, outdoor accurate survey information, you would really probably want a differential GPS system.
Got it.
Where the VIO in that case would probably help you hold position and fly super stably, and and not drift around with even the errors in the differential GPS.
Yeah.
But you would eventually, well, I mean, what the maps look like after a while. After a while, they're skewed off into the and so the GPS grounds you with an absolute position, whereas computer vision is really good for the relative position.
Right.
And so here starts to bring some of that to life. So we have on the upper left, we have an April tag, which is not very securely fastened to the wall, so it's probably not that accurate, but it's there and being recognized. And so that is, in relation to GPS, you can survey an April tag or a fiducial marker in the same way you could that differential GPS reference base station. If you know where that April tag is, it can provide you actually with an absolute location, say here's in a house. And so in the upper right, we're showing our debug display for VIO. And so obviously there's an XYZ, which is the position of the position of the robot. And then we have on the left of that screen, I don't know if I have a mouse cursor or anything, but on the left of that screen, there's a Q and a %. And so we derive actually a quality metric based on the covariance, number of features and the covariance presented from the Kalman filter in the VIO system. And I know we're going deep here, but that's actually the point of the quality system is to provide a simple metric that says how well the VIO system is working based on number of features and so forth. And so that's super helpful. It's because environments change. If you fly over water, for instance, it will not work because there's no good stable features.
Right.
So now what
for
about
beginners who are looking at this? I think it is worth mentioning that if you're building, robotics or drone application, an easy way to kind of cheat is use these tags called April tags, which you can put at various places. And it's very easy to detect that. OpenCV has a function out of the box to detect this. And it will also, so it detects the ID of the tag. So you can say that this tag was placed at this location and some other tag was placed at some other location. So you will accurately know where you're located by just reading these tags and the size of the tags, etc. So that's a very common technique used in warehouses also. They would have, like when a robot is going in a warehouse, on both sides, they would have a series of tags, and the robot would know immediately just by reading the tags where it is located. And that helps a lot in real world applications. But even when you are building some toy applications, you can vastly simplify your navigation, etc., by adding these tags to the environment.
Absolutely. Yeah, that's absolutely true. And then in that case, assuming you can't see a tag all of the time, a VIO-like system would be what would guide you between the tags.
Yeah.
And so then extending that, well, what if it's, the bane of every computer vision engineer is what happens at night. So what happens in the dark. And so here we're showing, we've mounted some IR LEDs, and the image sensors we're using are IR sensitive. So for this, you can kind of see in the debug displays, it's a fisheye sensor. So it's a single sensor fisheye, which we calibrate using OpenCV calibrate function. And here we've got an LED light. And so this is just demonstrating what happens what happens in a dark warehouse without the lights. So we can add LED lights to the drone. There's the green light, I think, is just left, but we didn't cover it up or anything. Oh, you can see you saw those two red eyes pointing at you. Those are the LED lights that are projected on the drone. And then hopefully we go back to the debug screen here, and you can kind of see that the features are still being tracked. Yeah, here we go. The features are still being tracked, and it's still flying in a stable fashion.
So, important question here with the spooky lighting and everything. Is the software and hardware able to avoid Michael Myers from the Halloween movies?
That's an important question. I suppose if he has good features and there's
I mean, you could train it on like an old William Shatner Halloween mask, and it might work.
Yep, absolutely. So yeah, and so here actually you can see, and a big part of this, I wish I had included that in this talk, because it is so important when you're building these whole systems, is you can kind of see at the bottom here, exposure and gain. It's really important, actually. We have to spend a lot of time on auto exposure. So we have a custom computer, a custom computer vision aware or computer vision sensitive exposure algorithm, because your traditional ISP or image signal processor found in these chips that are used for smartphones, they want to change really rapidly, right? They're really designed for you to pull your phone out of your pocket and take a video or take a picture, and you want instantaneous response, and that's terrible for computer vision. You really want your features to change slowly, right? You're performing a frame-to-frame tracking. Now, the flip side, of course, is if somebody does actually shut off the lights, you still need it to respond quickly. So there's like a hysteresis involved, and we've spent a lot of time on exposure over the years, which one might think of as a solved problem because you don't have to worry about it. But if you're really trying to build a robust system, you have to go in deep, and you can't rely on the basics and the default.
Right.
So here. And then extending those capabilities further, some of these are obviously pretty smartphone videos, but trying to show that it's real as well. These are not polished marketing videos. These are engineering videos. But in this case,
there's something to be said for that. That make it look a little bit janky so people know you're not screwing with them.
Right, exactly. And so in this case, we have two image sensors going concurrently, not in a stereo fashion, but actually in more of a, I don't know if the correct term would be binocular, but you can see on the far left, there's an image sensor pointing out at about 45 degrees. And on the right side of this UAV, there's an image sensor pointing out at about 45 degrees. And so this is actually back to that exposure problem for transitioning between light and dark rooms or going from outside into inside. It's actually a really tricky problem because your exposure is going to focus on the dark parts, or I'm sorry, on the wall. Say if you're going from outdoors and inside, your exposure is going to focus on the wall that's around the doorway, you know, that has all the interesting features. And then the moment you transition in, the lighting has changed significantly and you've lost all the features you were previously tracking. So this system here that we're developing is in an attempt to handle both of, or handle that, where if the front sensor is no longer tracking, the rear sensor is still tracking, at least while the front sensor can catch back up after a couple of frames to resume tracking as the large exposure change takes effect.
Are the HDR, now they have HDR video cameras, right? Are they very expensive, or they have other problems?
So that's a great question. It's more about, if you imagine like a 50, I wish I had a video of it. If you imagine a 50-50 scenario where there's bright sunlight and the walls that you're outdoors and the wall of the building is super bright and the sun is shining on it. The
Right.
exposure and gain are turned way down. And so
Right.
that doorway that you're trying to fly into just looks like a pitch black rectangle.
Right.
And
But
so
won't HDR solve that problem? I mean, because it takes multiple exposures and fuses them, will that not solve the problem to some extent?
that is an interesting approach that we've talked about, something similar where we actually run the sensor at a higher frame rate, and then interleave exposures,
Right.
kind of like an HDR, but actually just run two trackers.
Yeah, I mean, not exactly, because it's still moving, right? So it's not 100% aligned, but still maybe enough.
Yeah, I think you'd have to treat it as two trackers because you would have motion blur. These are moving. So even though this is trying to hold steady here, you know, it's trying to hold steady here, it's still moving. And so if you were trying to combine two frames, I think you'd have motion blur.
Right.
And so then
But even if you track them as two separate, right, you're running the sensor at two different exposures, and I don't know whether they can switch so quickly between the frames. If they can, like one is shot at one exposure and the second one is at a different exposure. Exactly. I don't know whether that switching can happen so quickly at say 60 or 120 frames a second. Then you have like as if you're looking at the scene with two different cameras at two different exposures.
Yeah, that is definitely one of the topics we're pursuing. But it's work. It's not easy.
No, it's not easy. I was wondering whether it is even possible. I don't know enough about the speed of these exposure setting changes, whether it is able to do it at 120 frames a second, the switching can happen.
I think we have, that's a good question. We've definitely tried at 30 frames per second, changing the exposure every frame. I forget, one of them you can change quickly, and between exposure and gain, one of them you can change quickly, and one of them you can't. If I'm
guessing that gain you should be able to, right? Because gain is it's a electronic thing, right? You're just multiplying something, and exposure might be kind of mechanical, but I don't know exactly how these small cameras work.
That would be my guess as well.
Yeah, exposure is basically how long it is going to collect photons in the pixel well.
Right.
Whereas
And in
gain, I
large
think
cameras, it's a
there's-
mechanical thing, right? I mean, it depends on the
Yes,
size of, aperture size, which is
yeah.
mechanical. But in
But-
these small cameras, I don't know enough, unfortunately.
Yeah, there is definitely not mechanical. Yeah, it's basically how long is that photon well left open
Yeah.
to collect photons.
Right.
So it's a cool topic, and because of the way we spend a lot of time on these drivers.
Right.
I'm
So
showing you
Andrew, one of
the
our
outcome
viewers,
yeah,
one of our
go.
viewers, Andrew, says that it depends on the camera module. Some can do thousands of frames per second. So it's interesting to know, because Andrew mentioned it to hosts and panelists, not to the entire, to everyone. So I just wanted to bring this out.
Yeah, so in this case, in this demonstration right here, they are OmniVision 9782 sensors, which are global shutter,
Okay.
1280 by
Yes,
800.
super well, often used sensor for sure. That particular model of OV you see pop up a lot these days.
Yep.
Yeah.
But it's an ongoing topic. It's a very fun topic, but it's also complex and requires going very, very deep in the system.
Right.
And which we do. I mean, we have people working on NIFI drivers every single day.
Definitely.
Okay, so here's what we actually have a bunch more to talk about. So I'll try to keep going through some of these videos. But so this is now starting to pull together multiple VIO systems. We have a comparison between the one we've been using in the past that we leverage from Qualcomm. We call that QVIO, and then we have here we're using a platform or a system called OpenVINs to navigate through. This is again back to being a ground rover. Unfortunately, as the video progresses, there's latency that starts to build up, and they start to render at slightly different times. But then this is fed into here. This is the other side of the right side of the screen is the Q ground control system, and then on the bottom, which is a common platform for controlling and flying drones. I wanted to highlight. So then on our system here, in the bottom right, we have our CPU monitor, somewhat like top, but since we're using an embedded SoC, there's frequency scaling, and top does not account for frequency scaling very well. So we have so why is this program taking 80% of the CPU? And it's not. Your CPU is scaled down too low, but or not too low. It's doing its job, but. And so we have a little program here that takes account frequency scaling, and you can actually see that even though we're running these multiple visual inertial odometry systems on the platform, we're not using very much of the overall system. These are background services running, and then more applications can be built and developed on top of that. And that's with two of them running concurrently. So, and then further advancing, where's a lot of this going back to maybe nighttime operation or different operation. This is a thermal sensor starting to run tracking and so forth on a thermal sensor, so that multispectral, multimodal tracking will be ultimately how these things become more and more robust.
Also, it looks like a Nine Inch Nails music video from 1996.
Yeah. That's nice. That's nice. Okay, and so ecosystem around some of what we're doing is we actually have benchtop systems. We have pre-configured flight decks that have, say 6 image sensors built in that are ready to go develop obstacle avoidance and visual inertial odometry and AI algorithms and so forth. We of course have OpenCV pre-installed and PX4, ROS, and a number of packages that really help accelerate development. And we have these little development platforms that one can go really. As far as I know, we're really the only ones that have these fully programmable open architecture UAVs out there to go do development. We sell a number to many university researchers throughout the world. Actually, it's very interesting. There's a whole business out there just in selling programmable drones that can go do computer vision and go build new applications on top of it.
Yeah, that's awesome. People are going to ask, so I'll get out ahead of it. What flavor of ROS? What release of ROS are y'all on?
Yeah, that's a good question, and I probably won't be able to answer that as well as I should. We have on there, I think ROS 1 is there pre-installed, which the current iteration is Ubuntu 18 based.
Okay.
So whatever would line up with that, if it's Noetic maybe. And then OpenCV, or I'm sorry, ROS 2, you can just do an apt-get install ROS 2. And but we do plan to incorporate, we want to move to ROS, I'm hoping this summer, we want to move to ROS 2, and we want to support that much more robustly than we are currently doing. Because it's definitely a better architecture. I mean, there's like really significant improvements with
yeah,
ROS 2.
they did a whole, like, it's an overhaul. It really is a big upgrade for sure.
Yeah, absolutely. And so then here now, as we move more into obstacle avoidance, let me know when we're running out of time here, because I want to get to the.
Yeah, I'll get out the big cane and pull you off stage. You got time, don't worry about it.
And so here you can see we have stereo sensors on board, and this is a disparity map for depth, which starts to build the foundation for obstacle avoidance and depth mapping. And so, oh wait, that's the news. And of course, calibration is incredibly important. This calibration system we have is built really entirely off of OpenCV, and so we're running the stereo calibration on target here with a predefined checkerboard. So what's important here is that the system, like any calibration system, there must be a ground truth. In the stereo calibration system, these checkerboards are often the ground truth, and then as the user here is moving the checkerboard throughout the system, it's going through and capturing the different images it needs to go run the calibration. And so then we run all this on our.
Everybody knows the calibration dance.
Yeah, exactly.
Well, they do, but they don't use it. They forget to. I like the interface because it's guiding people to do specific things. Usually, if you tell them, "Oh, you can take it under just about any orientation," they don't do it systematically, so they don't cover the space, and they don't get the results. I like this interface.
Yeah, you gotta get those super up close, distorted ones from the sides. Otherwise, you're not gonna get good calibration.
Right.
Yep. Yeah, and it paused very fortuitously right on that screen.
Yeah.
That's right. The skew parameter there. And to move these forward here. There we go. Okay. So now, we talked about visual inertial odometry, and we talked about stereo cameras and calibrating the stereo cameras. This is a bit of an eye chart that I'm not smart enough to explain entirely, but effectively, this is how the system works with all of the transforms. So each thing in blue is a transform as it moves throughout the, our matrix multiply of the data as it moves throughout the system to end up getting it into the frame or the position that relative to the center of the drone, so that the drone knows where it is and what obstacles are out there in relation to the center of its body, of the drone's body. And so what happens when you pull all of that together is that you can do things like this, where we're going to go fly full speed ahead at this tree. And the drone reacts.
Nice.
And stops appropriately and doesn't crash into the tree. And so you can see on the sticks there, he's literally just pushing it forward as fast as he can, and it stops automatically.
Yeah, talk about a smoke test,
Yes.
Send it headlong at a tree. Yeah.
And there's also, we haven't implemented this feature entirely, but you can see UAVs out there that'll do follow me, or follow a person or follow a biker and so forth. And so here we take that depth map from the stereo sensors, but then combine it with this probably MobileNet or some other deep learning technique, but a single shot detector, and fuse those two. And so now you know where this person is. You can see it's classified as a person, but you also know the distance. So in this case, we're saying it's 3.3 meters from the drone. And so then, of course, once you have the knowledge of what you're tracking and how far away it is, you can go follow it. We also incorporate another type of depth sensor, which is a PMD time of flight sensor. And so here this actually shows that we can run two at the same time. This is won't get into the details of how the time of flight system works, but it's like a mini LiDAR. But we use these instead of LiDAR because they're super lightweight. They only weigh 3 grams, which weight is what drives almost everything in unmanned aerial systems. And this one, I think, has about 110-degree field of view. You can see the warping a bit on the depth map. So in this case, we're ingressing two of these sensors, two of the depth sensors concurrently, and then we can make use of that information as well. These time of flight sensors are much more aligned for indoors. And so then you can see this is a little drone that has that same depth sensor on there. Now it's built out a full 3D map. Now we're getting into the Minecraft and VOXL territory. And we're going to tell it to execute a little plan. Right, we're clicking on the web browser here and saying, go to this location. The plan should be generated, and then it flies.
It's pretty sweet. So this map is being built on the kind of in real time, and then you're able to put a flight plan, without having to redeploy or do anything crazy like that. It's awesome.
Exactly. And there's Satya's April tag. Now this, jump ahead a little bit here. Okay, so now this is a more polished video that pulls everything we've talked about together. So in this case, you can see in the bottom right, that's our third person view. We'll pull up the first person view at some point, but on this, what we refer to as our web portal, that's a web server that's actually running on the drone. So all the processing is actually being performed on the hardware that's on the drone. There's no processing being performed on this computer other than just rendering this display.
Yeah,
so
that's awesome.
The whole thing, it's a flying supercomputer, full SLAM system, and performed all this 3D mapping. Now, in this case, we flew the drone around to generate the map before the video started. But what we're doing here is from the UI, selecting a point off in the distance here, and we have obstacles, cluttered obstacles, and you can see the archway. You can see the archway then represented in the map, and then we click on the point, and then we say plan a path. And so in this case, it plans. I think in this system, it's planning 3 paths. It first plans what's referred to as like an RRT, which is like a pretty kind of brute. It's got to plan like a really coarse brute force plan. I want to get from here to there. What's going to block me? And then there's 2 more steps where we refine it and smooth out that plan, because it looks really janky to like go station to station to station. Just flying. So you can see that black line is the course plan. Then you see it starts to build out these smoother plans right in front of it effectively to go navigate nice and smooth to that location. And so this really pulls in that full 3D mapping and pulls in the full 3D path planning use case all together in a complete sensor fusion system. So it's really a flying sensor fusion system where we have the image sensor, the fisheye image sensor for the tracking, that's fused with the initial measurement unit to generate VIO. Then we have the depth mapping from the time of flight sensor. When you take that depth map and your location from VIO, then you can build out these voxel maps. So that's how these the colored structures in this map represent these voxels, which are 3D pixels. And so again, we take the depth map, we know where we are from VIO, we take that depth map, combine them, and then generate this 3D map that we can then plan, generate paths, plan through, and then go execute and follow those paths while flying.
Extremely cool.
That's really cool.
And then lastly, we've built an even smaller version that we just announced yesterday or the day before. And so this one's only 11 grams. See, the train's even excited about it. So this one's only 11 grams and has all that same exact horsepower. A little less IO, so a little bit less image. It can support 4 or 5 image sensors instead of 7 on the larger version, and a little bit less IO. But if you're trying to build something really, really small that might navigate a tight, cramped warehouse, for instance, then this is, you know, best in class platform to go do so.
Or patrol for you know, Michael Myers, Jason Voorhees, those sorts of things.
Do you also have do you also sell the whole system by any chance?
Oh yeah, absolutely. It probably didn't. I think I skipped. I tried to keep it more technical and less marketing, but the
people want to know.
Absolutely. And so let me jump back here. These videos are hard to bust through. There we go. So yeah, so what you see on the right are the complete systems that we do
Oh,
sell.
right. Yeah.
Yeah, and so
it slipped me.
No, that's okay. That's okay. Yeah. So the benchtop system we haven't quite launched yet, but we plan to this summer. That's a little bit of a messy version of it, but we're gonna have so a lot of our customers are building their own drones, that's like really our intended market, right? And we also have a good market around folks that are just buying our drones to go develop computer vision applications. But a lot are really going to build their own, you know, drone that does new and interesting use cases. And so these benchtop systems really kind of help them with system architecture, right? These are complex systems, and it's not fair to say, oh, just plug all this stuff in and fly. That's not like a realistic scenario. You've got to go build out the system from, you know, the ground up. And so we offer those at various steps. You know, the core components, the benchtop systems, the flight decks, which are pre-configured and pre-calibrated, so that you can see this work like right out of the box. And maybe you can mount it on a drone yourself, but you still need to kind of go through the effort of building your own thing. And then we have our Sentinel. There is a full up platform with forward, and it has the GPS denied navigation, forward and rearward stereo sensors. And then Starling is what you saw in the video, that's more attuned for indoor outdoor transitions and indoor warehouse mapping. And it has that time of flight sensor on it.
So the dev drone, Sentinel dev drone that you have, what is the flight time?
That would probably flies 20, 25 minutes.
Okay.
In that range, something like, yeah.
Yeah, and it looks like according to the website here, the Sentinel there will run you $3,599, and the smaller one, where is it here?
That one's not quite launched yet. You're getting
now y'all not launched yet. I got you.
But it'll be a little bit cheaper.
Okay.
All right.
Cool.
The target is under 3,000.
Yeah, I mean that's for all the tech that's packed in there. It's really impressive. Yeah.
Yeah.
Awesome.
Absolutely.
Yeah. So shall we do? I guess we'll do our giveaway here, eh?
Yep.
Before we get to questions and answers. Yeah. So thanks so much for that awesome presentation, Chad. I learned a bunch about the state of the art of autonomous drones. I hope that you out there also learned a lot about the state of autonomous drones, because now comes our trivia question. Folks in the Zoom chat here will now have the chance to win the OpenCV course of their choosing. You can find out what courses are available by going to opencv.org/courses. If you have won in the last couple of months, please do not answer and give someone else a chance to win. I am going to ask a trivia question now based on the presentation we just saw. Answer in the Zoom chat window out there, audience, and the first person to answer correctly will win that OpenCV course of their choosing. So talked a lot about open source today. There were a lot of different software packages, for example, in the ModalAI ecosystem. 4 in particular were called out on one of the slides showing off the latest and greatest hardware there. 2 of those were Docker and OpenCV. What were the other 2? Answer both at the same time. All right. Vineet, super quick there. The answers we were looking for were ROS and PX4. You are correct, Vineet Sharma. Please send one email to phil@opencv.org with the course you would like, and we'll make sure that you get access to that in your course's dashboard. If you didn't win, good news. You can still learn stuff by going to opencv.org/courses and checking out what we have available there. Invest in yourself, level up your education, level up your computer vision knowledge. There's machine learning courses. You can learn how to use PyTorch, et cetera, et cetera. That's opencv.org/courses. Thanks again to our sponsor at OpenCV.ai Consulting, who kind of covers all of this stuff for us. If you want consulting, need consulting, maybe aren't sure if you need consulting on computer vision, machine learning, artificial intelligence, everything from soup to nuts production, go to OpenCV.ai, contact the team, chat with them, see what we can do together. It always helps to reach out. So thanks again to our sponsor. We've got a bunch of great questions here. So Edgar Lai would like to know about the battery consumption of that Sentinel drone in particular, Chad. Do you have any more information about that for Edgar?
Yeah, so the Sentinel should fly for between 20 and 25 minutes, and then the Starling, which is the smaller platform, will actually fly for over 30 minutes, and the Starling will be out here shortly, hopefully in the next 2 months or so.
What kind of what kind of actual consumption, like, and how big is the battery in those things that, you know, people are just interested in the weight to performance ratio, of course, as always.
Yeah, generally, as you go larger, you become more efficient. The smaller one is actually benefiting from being a little bit more stripped down and designed to fly for a bit longer at that kind of weight class. In the UAV space, you generally target about 1/3 of your overall weight per battery. So on the Starling there that we showed, I think we have 2 18650 cells, and also it's lithium ion. So whereas the Sentinel has a 4-cell, or actually 3-cell lithium polymer pack. I don't remember off the top. It's probably about 3,200, 3,500 milliamp hour 3-cell pack. I think would be my guess.
Sounds reasonable to me.
So what's the weight of
Stan.
these batteries? Sorry again.
Oh, so we're saying generally they're about 1/3 of the weight of the overall platform.
So the whole platform was the drone is how much?
So I think the takeoff weight for the Sentinel is about 1,200 grams, which would be in the order of 2 pounds or so. And then the Starling that we showed is 275 grams, or about half a pound.
So it'd be like 400 grams or something like that for the battery, give or take.
On that Sentinel, yeah, that's probably about right.
Cool. Thanks for that. Sean
And that's
Wong
for
would like to know.
doing.
Oh, go ahead.
Sorry, and that's for. So that's the kind of battery you would need for doing some of these. But it's also the flying of the drone. So it's quite a lot of mechanical work also, right?
Yeah, keeping the drone in the air is 95% of the power consumption.
Got it.
Yeah,
okay.
Keeping in mind that it's also running that whole web server on itself as well, which is, you know, not nothing.
Yeah, it's just that fighting gravity consumes an incredible amount of energy. It is.
That's right.
It's really hard to stay in the air. It's really energy consumptive, I should say, to stay in the air.
That's a great quote. We'll probably run that at the top of the show. Xiang Guang would like to know, what's the resolution of the infrared cameras on that one?
Well, in that case, so they're IR sensitive. The cameras we showed were IR sensitive, meaning they don't have like an IR cut filter to actually filter it away. The ones for computer vision on the Sentinel are, we have stereo VGA global shutter forward, stereo VGA global shutter rearward, and then a VGA fisheye for visual inertial odometry, and then there's a forward 4K RGB, like a 12 or 13 megapixel RGB sensor just pointed forward.
Word.
And they
Ethan
all
would
run
like
concurrently, so which is
Yeah.
cool. Like
Wow.
from a vision processing and sensor fusion thing, they're all running concurrently.
Yes, thank you for that. Ethan would like to know, is there any work done on the drone being able to go recharge itself if it runs low on battery? He's kind of interesting question.
Yeah, there are definitely folks doing that. There are definitely folks working on that. It's tricky. It's not like maybe the part that we play, not the role we play in the industry. It's the box, to house a drone. You see some of these companies have these drone in a box platforms. That box is a robot itself and has computer vision processing and has its whole thing going on. And that is just as much work as actually building a drone. So it's
a whole other product.
Wrong answer, Chad. Wrong answer. If you were Elon Musk, you would show that the drone goes and swaps out the battery. It just lands on the battery, swaps it out, and then takes off.
Right.
Yep.
Right.
and then 10 years later, it still wouldn't exist.
Right. Exactly.
No,
Maybe I'm too honest.
Yeah, too honest. Not a virtue that apparently this industry cares too much about, but I do appreciate it. Got a few more good questions here. ROC would like to know, is there a built-in module for going between different coordinate systems? For example, like north, south, east, west compass versus like digital coordinates?
Well, we do, as part of the SDK, we have this package called VOXL Vision Hub, and all of our code's open at code.modalai.com. And so in that, there's a whole section dedicated to all these transforms from all the different sensors to all the different coordinate frames, ultimately resulting in the body of the drone to go the center of the body of the drone, so it can go fly and achieve what it needs to do. I don't know magnetometer necessarily specifically, but I would assume the PX4 itself might be accounting for that, now that I think about it. On the vision side, though, we definitely spend a lot of time on that, on solving those transforms.
Cool. A LinkedIn user would like to know, does the software, does the package come with any pre-trained models, say for like semantic segmentation or general object tracking?
Absolutely, yeah. So we have what's referred to as the VOXL T-Flight server or TensorFlow Lite. And so in there, there's 7 or 8 models that are ready to go. Now, we don't do anything special. They're the stock, the stock models trained on the stock, Coco or whatever data set. So, but, from there, one, that understands, follows Satya's courses should be able to train the model. And
well, the most important thing, the most important thing for these
synergy, I love
these
it,
models is that a proof of concept, right? When you can see that something works, right, you can figure out one way or the other that, okay, I'll be able to run this object detector at this speed, right, on the device. So you're not guessing. You have an example to go by, right? That's the most important thing. And thanks for adding that to the SDK. People. One example is all you need, right? A few examples, and that's all you need.
Yeah, and there are so many great resources for learning this stuff, not just OpenCV courses. There's also learnopencv.com, which I know the guy that runs that place if you want to check it out. He's a little bit sketchy, but no, it's Satya's website for those that don't know. I mean, we're pushing up on time. Folks, if you have more questions here that we didn't get to, a great way to reach out to us with those is at the end of the show, probably tomorrow, you'll get a little email asking you what you liked about the show, a little comment card type of thing. Ask your question there and we'll do our best to answer it for you. If we don't know the answer, we can pass it along to Chad and hopefully he'll be able to solve any questions you have. Yeah, next week our guest, I believe, will be talking about with 7 Sense about OpenCV facial recognition. Satya, you got any final thoughts for us before we go home?
No, that's it. Thank you so much, Chad. Where can people reach you at?
Yeah, so the easiest, well, I'm on LinkedIn or, for ModalAI, just generally, I think it's modalai.com/contact. That's a great place to start and learn more. But in general, we, docs.modalai.com, we update multiple times a day. Forum.modalai.com, we answer questions all day long. And code.modalai.com, you can see our full SDK and go, make use of it. And we love hearing about what folks are building with our VOXL platform.
That's great. That's great. Thank you so much. Just one announcement. Our courses, the Stable Diffusion course that we are working on, the first course hopefully would be released on this Monday. And there was a little hiccup with the course. The hiccup was that, when we started building this course, Midjourney had a free version. Okay, now they don't, which is okay. We thought that we still have the open source version of Stable Diffusion that people can run on Colab. And now Colab prohibits people from running Stable Diffusion, any web UI. They prevent running those things, right? Because I think it was killing them in terms of cost, that now regular folks are able to use without any programming background. They are able to use the GPUs, and so that's banned. So we are trying to figure out what to do, about that. So that's a little hiccup, but we'll release the course soon.
Why does Google hate fun? I don't know. Yes,
All
thanks so
right.
much. Hey, go ahead,
Yeah,
Steve.
Phil, go ahead.
Okay. Thanks so much, everybody, for joining us. We will see you next week. Same bat time, same bat channel, 9 a.m. Pacific on Thursday with another great episode about OpenCV facial recognition. We hope you join us. Take care of yourselves out there. Take care of somebody else if you can, and have a great day wherever you may be.
All right. Thank you so much.
Thank you all very much.
Thanks so much for watching this episode of the webinar. Please hit that like button, subscribe, and don't forget to tap the little bell icon to be notified when new episodes drop. This week's episode was brought to you by OpenCV Courses. Learn computer vision and AI from the best at opencv.org/courses. If you'd like to be in the audience next week, subscribe to the OpenCV newsletter.